Hello friends, welcome to my channel. Let's have a look at a newly appeared problem. Problem 2527. Find Xor-Beauty of Array. In this video, we're going to share a solution based on the analysis using symmetry or commutativity of the bitwise and or operation. And also we're going to use the annihilation property of XOR or exclusive OR. So first, I'll read through the problem statement to digest the requirement, and then we do the analysis, and finally we share the shortcode. So first, the problem statement. We are given a zero-indexed integer array called nums. The effective value of three indices I, j, k is defined as the following. So nums I, bitwise OR with nums j, and then the result bitwise add with the nums k, right? So the exclusive OR beauty of the array is the XOR of the effective values of all the possible triplets of indices I, j, k, where I, j, k runs between 0 and n. So 0 inclusive and n exclusive. So we are required to return the XOR beauty of nums, the given list or array. So here are two examples. So you can analyze example 1. So in example 1, so the length of nums is 2, right? So in the explanation, it lists all the possible triplets and then gets the effective value and then do the exclusive OR for all the values. So the output for example 2 is 34. So after our analysis, I guess it's quite easy to understand the output for example 2. So before we do the analysis, let me also emphasize the constraints. First, the length of the array is bounded above by 10 to the power 5. So this number is a decent large number. In other words, we should analyze the problem rather than doing the problem in a brute force way. And also we know that this list or array is not empty, right? So the elements in the array is positive integers, right? Because it's greater than or equal to 1. So here is also a upper bound. So with that said, we are ready to do the analysis. So here, this problem, I guess, there's more for analysis, but less coding. So because once we get the idea or digest the overall analysis, then writing the code is a piece of cake, I would say. So here I wrote like this. The method, I term it as using symmetry or commutativity and the annihilation property of XOR. So here the same as you realized, so it's very straightforward. First, as we mentioned, so this is a very straightforward problem if we are very familiar with the bitwise operation properties. And for this problem, so the following properties come into play. So the first one is the annihilation property. So in other words, A exclusive OR with itself will give us 0 for integer A. So here we can restrict A to be non-negative integers. For example, you can look at the atom 2 in the constraints. And secondly, the commutativity property. So here, so the AND, bitwise AND and the bitwise OR are both commutative. In other words, A or B equals B or A. A and B equals B and A, right? So the above two observations and actually plus symmetry arguments can help us reduce the problem to the exclusive OR result of elements in the given list, nums. So here, let me walk you through the procedure and or the thought process. So first, so let's fix for each index k. Let's fix it, and then we consider two different indices I, j. So we assume I does not equal to j first, and then they corresponding to two triplets, that is I, j, k, and j, I, k. If you consider symmetry or permutation for each index k. So these two triplets, actually, their contribution is 0. The reason is that, so we compute nums I and or nums j and nums k. Then we also consider gi, right? So if we consider symmetry, so let's see gi here, right? So this corresponds to two different triplets. And then because nums I and nums j and nums j and nums I are the same, then if we do add operation with another nums k, they're still the same. So we are doing exclusive OR for the same number, so we get 0. So this is the first atom. Therefore, we just need to consider the case I equals to j, so which corresponds to one triplet, right, for each index k, that is I, k, right? Or correspondingly, we consider the following contribution for indices I and k. So numbers I, and nums k, right? So but nums I or nums I or itself, it's still itself. It reduces to nums I and nums k. So we just need to consider the contributions of these factors for different indices I and k. So now let's look at the second step. So we continue to reduce the problem. So let's first consider the case if I does not equal to k. So then we know the corresponding to, we can consider two pairs I and k and I. We reverse that. In the original triplet format, this corresponds to RIK and KKI. So we have their contribution is nothing but, the first one corresponding to nums I and nums k, and the second one corresponding to nums k and so here is add nums I. So then we want to consider the exclusive OR of all such factors or such formats. But the add operation is commutative, right? So nums I and nums k equals to nums k and nums I. So if we do exclusive OR for these two, so we are going to get 0 again due to the annihilation property of exclusive OR, right? Therefore, we just need to consider the case I equals k. In the original triplet, it corresponds to consider the case for I equals j equals k, and the corresponding format. So this is the thing we want to consider, right? Nums I and nums I, nums I or nums I and nums I. So together, this is nothing but nums I itself, right? So with the first two steps, we know that in conclusion, we just need to compute the elements exclusive OR result for the list nums given, right? So once we up to this step, so we are ready to write the code. So that is actually a piece of cake, obviously. So first, we are going to initialize a result variable. So we are going to return its final state. So we just need to scan the list nums, in other words, traverse it. So for y in nums, right? So we do this exclusive OR with respect to y. Then we just return the final state. So that's it for a solution format to this problem. So now let me first do some check. Yeah, it passes one example. Now let's look at this one, right? Now you can easily understand why we have an output 34. So we just need to consider the exclusive OR of these numbers. So now we are in a position to test all the cases. Yeah, it passes all the cases. So if we consider if we regard each exclusive OR operation as a unit term, so this is nothing but ON, where term complexity, where n is the length of nums. So with that said, I guess that's about it for this specific problem, and also it's the end of this video. So you're welcome to comment and check out other videos in my channel. Thank you.